Well, greetings and welcome to Naughty Notes. Well, here's checking on our practice exercises that go with that lesson 110, where we were graphing in class and finding rigid transformations. You'll find this pages 74 through 76 in your textbook, McGraw Hill. So let's make sure you got them right. Let's have a look over here. I like this. We have a nice illustration here of the four ways that we transform figures. And the very first one, A, we can say that we're going to slide it over. And we call that very simply a vector translation, or maybe a glide transformation. See, this is the path that we're traveling. Or just slide, something like that. But it's certainly a rigid transformation because the image A prime, B prime, C prime looks exactly the same as the pre-image ABC. Now our second is over here on B. If I were to take this and rotate it like that, look at that. Well, that's clearly a rotation. In this case, it's rotating around the point A. And that is also a rigid transformation. And let's look at C down there. And I'm looking at C, and I can see that I'm flipping it or reflecting it across this axis. So we reflect across an axis, and that again is a rigid transformation. Same shape, exactly same size, just in a different direction. Now, of course, you've probably figured this one out. If I look here, this is a little different. If I take this, this is still a transformation. However, this is what we call a dilation. A dilation because this figure, the image in this case, is bigger than the pre-image. You might say it's an enlargement. And if you notice over here, this is the center of dilation. So you can see that this is the one that does not fit. Okay? All right, let's go to the next page, 75. See how we're doing. Now, I like these definitions of congruence. Let's go through these. A, two figures have the same shape, they are congruent. Well, hang on a second. These two figures have exactly the same shape. They're both regular pentagons, but they are not congruent. If I were to put one over the other, it's not a perfect fit because one is bigger than the other. So the word we're going to use for this is similar. These are similar polygons. They have all the same, they're both equilateral, and they all have, and each pair has congruent angles to each other. Their corresponding angles are congruent. They are similar. We'll have a whole chapter on that. How about this one? Two figures have the same area. Well, I've got that depicted right here with a couple obvious rectangles, a 6 by 2 compared to a 3 by 4. Well, you can even count the squares. You got 12 in each, and that's the same area. But these figures are not. They are not congruent. Not only are they not congruent, they're not similar either, because they have a different, in rectangles, we would call this an aspect ratio. Just like in your TVs, the old widescreen versus full screen days. Maybe your parents remember that. Okay, so these two are gone. All right, we've eliminated those two. Let's have a look at the next one, C. If there's a sequence of transformations taking one figure to another, they are congruent. I kind of like that. But there's, but this is actually kind of funny. They've got C and D here. I would sure hate this. I would not accept this as a test question. If there's a sequence of rotations, reflections, and translations that take one figure to the other, then they are congruent. These two seem to say the same thing, but I'm guessing that they're trying to trick you here because a transformation that they could be talking about would be a dilation. See, they're specific here, saying it can only be rotations, reflections, and translations. Now, if you could argue the other side and say, hey, well, does that mean it has to have a rotation and a reflection and a translation? No, it doesn't. So I think the answer they're looking for is this one. But, you know, arguing is a good thing. I could argue for either of these, but I would never ask it in such a way. Just know that it has to be a rigid, and I guess maybe that's the better way to put it. Put the word in there. Say a sequence of rigid transformations. And maybe that would be more specific. But anyways, I just thought that was a little fuzzy on the question. So let's go to the next one. This is kind of simple. We're going to take this figure. You know, I think this is, I got messed up in your book. See, it looks like that in your, that's the clip I got from your book. So I tried to make it, and I said, oh yeah, well then you can rotate it. So clearly there's, we talked about a sequence of transformations. In this case, yeah, there's actually two, because you've got what they call a translation, or maybe you call it a glide transformation. I like to call it a vector, because I'm going to move it according to a path, and then a rotation. And certainly, if I were to put that point D somewhere, it's the D prime is going to be right in between C prime and B prime. It looks like it's in the exact middle, and you know, honestly, I think it is. We don't know for certain, but I believe it is, and close enough to the naked eye. All right, number 4. 4 was fun because we spent a whole day on this. You just don't know it. You know, this is the classic problem. Oh, that's not what I wanted. No, hang on. This is the classic problem for the circumcenter. You constructed a circumcenter by hand twice with a compass and straight edge. And let me explain that. You've got these points A, B, and C. Now I could enlarge this at any point, and I'll keep it about this size. Now let's suppose we connect them, these 3 random points in a plane, and then we do this. We do the perpendicular bisector constructions. Heavens to Murgatroyds, look at that. Now that's what you did. That's what you did on paper and pencil, and you see it would behoove you to use colors to keep track. For example, right, like right here, I'm looking at, say, okay, I'm looking at the perpendicular bisector of BC, so maybe I'll put in a blue pencil or something, and maybe I'll change my colored pencil so when I'm doing the other ones, it'll be easier to keep track. But regardless of how you did it, you came up with one point of concurrency, and it was right there. Now, that's what we did in class, and then we did it on, I had you do it on GeoGebra, so you've got a lot of practice with this figure. And this is what we were after. This is, of course, the center of the circle that contains the points A, B, and C. Now, I had at least one student point out to me, say, Mr. Manish, you only need 2 perpendicular bisectors. Yeah, that's true, but I asked you to construct all 3 for several reasons. One is that it's a check, and all 3 of them need to coincide. It's beautiful to see the 3 perpendicular bisectors coincide. And yeah, so I guess it's a testament to your accuracy, and it's a good way just to verify that you've been doing it right. I'd rather that than you just doing 2 of them. I mean, if you had certainty, like you're doing software construction, yeah, I guess 2 would be legit. But let's do 3 and make it, and just enjoy the math. Now, I'm going to clean this up a little bit. I'm going to get rid of this. No, I'm going to keep that. I'm going to get rid of all these constructions and just keep the circle that we made. And I'm going to zoom in on it like that. Okay, that's the result. This is the result of our circumcenter construction. Just like Magellan, we're going to circumnavigate the triangle. So now we're going to do this. You took the, well, I guess a little late on that. So you did that, and that was the very last circle you made. But now think about this. If that's where you put the needle of your compass, that is the center of the circle. That means all of these are radii, and all these radii are congruent. And that means that this point right here is the point that is equidistant from A, B, and C. So in the classic problem there, roughly the same distance. Well, of course, because you've got other considerations like traffic, whether it's streets and things, but right there, this would be the exact center, or the point that is equidistant from the 3 points A, B, and C. And that's kind of fun. So let's see. Yeah. Well, that was, you're going to see this in some kind of and some Canvas quiz, something or other. So it's important for you to know that this thing that you did, that this wild construction really came down to meaning this. So put that in your notes. Good to know. Ready? Okay, one more page. Now, construct a line through seeing one of these error questions. Perpendicular bisector of AB and then true. Is CD guaranteed to be parallel to AB? You know, I gotta stop. I gotta do this because this drives me nuts. You know, AB is a line, CD is a line. Our text is, no, like this. Our text seems a little soft on that, but language is important. So Han constructed this perpendicular bisector of AB. For what reason, I don't know. And then just put this random point C in there. Is that guaranteed to be parallel? Heck no. A couple things. I'm not crazy about this type of perpendicular bisector construction. I'd prefer that center to A passing through B. I know some people teach it this way. No, don't want to get into okay, I will. Because that way, in true Euclidean fashion, and you're going to see this fall apart, in true Euclidean fashion, when you put the needle on the A and gap it to the B, and you swing that arc or circle, then the compass loses its shape when it's picked up off the paper. And you put the needle on the B, and you can put it back to the A. Euclid was doing this without a compass that was rigid, that could hold its shape when you lifted it off the paper and put it back down. That's why, I'm just a little old school on that. I prefer that the construction looks like that. And then, of course, Hans got this point here, this random point here. This is just a random point. I mean, it's got nothing to do with making the lines, parallel. To make the line parallel, you'd have to do the perpendicular construction again from here. So, that's what we did. We did the perpendicular construction twice. If this line is indeed perpendicular to AB, but there's nothing that makes these two lines perpendicular. This is point C floating around here is just a guess. So the answer is, so we know that that's no good. No good. And we did that as an exercise, and I'll tell you, you guys did great. So there, hats off to you. Let's do another one. Oh, and I think this is the last one in the series. One of these fill-in questions when way back in it was lesson 1.5 that seemed like so long ago. All right, let's see what must be true. AD. Now, I didn't preview this one because I kind of thought it'd be pretty easy. But so, all right. So AD, AD equal BD. Well, that's just plain ridiculous. There's no saying where B is on this. So we can't even say which one's bigger. I know your author might say it's inside the circle, but okay, even if we use that, we can say that BD is not the same as AD. So this guy is bogus. Cross it off. How about EC equals AD? EC from here to here equaling AD. Well, hang on a second. First off, we know this is not right. AD is the diameter of this circle, and EC is clearly not, because from C to this magic point is the radius, and that's not doubling it. So those two are not the same. I'm going to cross that one off too. How about AC, DC? Well, AC and DC, well, hang on. I think we've got ourselves a winner. Let's put the little segment control in there. So from here, A to C and D to C, I'd say that's totally legit. This one's good. C is good. We know that. Again, we know that because the perpendicular bisector, well, it's two things. It's perpendicular and it bisects. That line, CE, chops that, the segment AD in half at C. So I think we got one so far. Let's keep going. EA to ED. Now, EA is the radius of circle A. ED is the radius of circle D, and both of them are congruent to the radius AD, which is going way back to the beginning, and we're going to give that one an absolute true. So again, this and this are the same. I'm going to mark them like that. So yeehaw, we're two. I guess we're 2 for 4 right now. And if you all remember, when we did this, we made ourselves an equilateral triangle. That's the construction for an equilateral triangle, by the way. And let's just construct a triangle and kind of keep it like that. Pretty. Now, ED, there's ED. Oh yeah, ED's over here. And DB, well, I see no connection between them. And again, that point B is kind of floating. There's no definitive location. There's nothing special about it. I don't see any connection there. So I'm going to have to cut that guy off. How about CB and AD being the same? CB. All right. And else, okay, so these are overlapping segments. From C to B is like that. And A to D is like that. Don't see it. For that to be true, that could be true, but if and only if BD was equal to AC, but we don't know that. And that would be just guessing. So that's going to have to generate a giant false. Remember, if it's not true all the time, then it's not true. So out of all those, it looks like we got ourselves 2 statements, and we've got them marked with tick marks up there, and that's it. C and D must be true. Must be true, and that was a nice little review, and I think we'll call it quits there. And I want to say see you in class, and thank you for watching Naughty Notes.